Our sun, the star at the center of our solar system, is a colossal nuclear furnace. It bathes our planet in light and heat, making life possible. But this seemingly benevolent star has a dynamic and sometimes violent nature. Among its most dramatic phenomena are solar flares. These are immense explosions on the sun's surface, like giant flashes of light. They occur when magnetic energy that has built up in the solar atmosphere is suddenly released. Imagine a rubber band being twisted and twisted until it finally snaps. A solar flare is a cosmic-scale version of that snap, releasing an incredible amount of energy in a very short time. This energy is equivalent to millions of hydrogen bombs exploding simultaneously. The root cause of these spectacular solar flares lies deep within the sun's complex magnetic fields. The sun is not a solid body, it's a giant ball of superheated plasma, an electrically charged gas. This plasma is constantly moving, churning, and rotating. Because the sun rotates faster at its equator than at its poles, its magnetic field lines can become twisted, tangled, and stressed. These tangled magnetic loops can protrude from the sun's surface, forming active regions known as sunspots. It is in these magnetically complex regions that the conditions become ripe for the sudden explosive release of energy that we observe as a solar flare. These are not just random occurrences, they are a fundamental aspect of how our star behaves and releases pent-up magnetic stress. When a solar flare erupts, it unleashes a torrent of radiation across the electromagnetic spectrum. This includes radio waves, microwaves, infrared radiation, visible light, ultraviolet light, X-rays, and even gamma rays. The most intense parts of this emission are often in X-rays and extreme ultraviolet radiation. Along with this radiation, flares can also accelerate charged particles, primarily electrons and protons, to nearly the speed of light. These particles, known as solar energetic particles, stream out from the sun. The flare itself is a localized event on the sun, but its effects can ripple outwards through the solar system, carrying significant energy far from its origin point, a testament to the sun's powerful influence. Solar flares are classified according to their brightness in X-rays as measured by satellites. The classes are A, B, C, M, and X, with A-class flares being the smallest and X-class flares being the largest and most energetic. Each letter represents a tenfold increase in energy output. So an M-class flare is 10 times more powerful than a C-class flare, and an X-class flare is 10 times more powerful than an M-class flare. Within each class, there is a finer scale from 1 to 9, for example, X1, X2, up to X9, and beyond for extremely powerful events like the X28 flare recorded in 2003. Understanding these classifications helps scientists and engineers anticipate the potential impacts these solar events might have on Earth and our technological systems. When a solar flare occurs, the intense burst of X-rays and extreme ultraviolet radiation travels at the speed of light, reaching Earth in about 8 minutes. This radiation is the first wave of impact from a solar flare. It primarily affects the Earth's upper atmosphere, specifically the ionosphere. The ionosphere is a layer of the atmosphere that is ionized by solar and cosmic radiation, meaning it's full of charged particles. This layer is crucial for long-distance radio communication because it reflects and refracts radio waves, allowing them to travel over the horizon. The sudden increase in X-rays and extreme ultraviolet radiation dramatically increases the ionization in the lower parts of the ionosphere, the D region. This enhanced ionization in the D region has a profound effect on high-frequency radio communications, which are used for aviation, maritime, and amateur radio operations, as well as some emergency communication systems. The energized D region becomes highly absorbent of high-frequency radio waves, preventing them from reaching the higher F region, which normally reflects them back to Earth. This results in a radio blackout, where communications over the sunlit side of the Earth can be completely lost for minutes to hours, depending on the flare's intensity. This is a direct consequence of the flare's electromagnetic radiation, altering the Earth's atmospheric properties, a clear example of our planet's interconnectedness with solar activity and its impact on vital communication networks. Navigation systems, particularly those relying on the Global Positioning System, are also vulnerable to the effects of solar flares. GPS signals are radio waves transmitted by satellites orbiting Earth. These signals must pass through the ionosphere to reach receivers on the ground. During a solar flare, the changes in the ionosphere's electron density can cause these signals to be delayed or scintillate, which is like the twinkling of starlight. This scintillation can degrade the accuracy of GPS positioning, or in severe cases, cause the receiver to lose its lock on the satellite signals entirely. For industries and activities that depend on precise positioning, such as aviation, shipping, surveying, and precision agriculture, these disruptions can be significant and even dangerous. Beyond communication and navigation, powerful solar flares, especially when associated with coronal mass ejections, can induce geomagnetic storms that threaten our power grids. A coronal mass ejection is a massive eruption of solar plasma and magnetic fields from the sun's corona. If a coronal mass ejection is directed towards Earth, its arrival a day or two after the flare can cause large disturbances in Earth's magnetic field. These geomagnetic storms can induce powerful electric currents, known as geomagnetically induced currents, in long conductors on the ground, such as power lines and pipelines. These geomagnetically induced currents can flow into power transformers, causing them to overheat, potentially leading to damage and widespread power outages that could last for an extended period. The month of May 2025 served as a potent reminder of our star's capacity to affect life and technology on Earth. Our planet experienced a significant solar event that captured the attention of scientists and the public alike. NASA's Solar Dynamics Observatory, our ever-watchful eye on the Sun, detected a powerful X2.7 class solar flare. This event, occurring as the Sun ramped up activity towards its solar maximum, was the strongest flare recorded in 2025 up to that point. It highlighted the increasing solar turbulence and the potential for disruptive space weather events that could impact our technologically reliant society in profound ways. The data gathered from NASA's Solar Dynamics Observatory proved invaluable in understanding the flare's characteristics and its immediate consequences. The X2.7 class flare peaked on May 14, 2025, at precisely 4:25 a.m. Eastern Time. The immediate and most noticeable effect was a significant radio blackout. This disruption primarily affected the sunlit side of the Earth at the time of the flare, impacting regions across Europe, Asia, and the Middle East. High-frequency radio communications, vital for various sectors including aviation and emergency services, experienced substantial interference or complete outages. This event underscored the direct link between solar activity and the functionality of critical communication systems, forcing operators to quickly adapt and manage the sudden loss of signal, a stark demonstration of solar power. The concerns raised by this X27 flare extended beyond immediate radio blackouts. Such a powerful burst of radiation also posed a potential threat to satellites in Earth orbit. Satellites are constantly exposed to the harsh space environment, and intense solar radiation can damage their sensitive electronics or degrade their solar panels, shortening their operational lifespan. Furthermore, the flare heightened awareness regarding the vulnerability of our terrestrial power infrastructure. While this particular flare's associated coronal mass ejection, if any, was Earth-directed, effects were still being assessed. The intensity of the flare itself was a strong warning about the potential for severe geomagnetic storms that could follow such powerful solar eruptions if they are accompanied by Earth-directed coronal mass ejections. The May 14th event was not an isolated incident during this period of heightened solar activity. Just a day earlier, on May 13th, 2025, another strong solar flare, an X1.2 class comet, had peaked at 11:38 a.m. Eastern Time, also causing radio blackouts. This quick succession of X-class flares, along with other strong flares recorded in January, February and March of 2025, painted a clear picture of a sun progressing towards the peak of its activity cycle. Indeed, even as of May 20th, flare activity was considered low, but with a newly active sunspot region beyond the northeast limb showing signs of strength, and a C5. 3 flare was the largest of 9 flares that day, reminding us that the sun's activity is a continuous, dynamic process. The sun experiences a natural cycle of activity that lasts approximately 11 years, known as the solar cycle. This cycle is characterized by a gradual increase in solar activity, reaching a peak called the solar maximum, followed by a gradual decrease to a solar minimum, During solar maximum, the sun's magnetic field becomes more complex and unstable. This leads to an increase in the frequency and intensity of solar phenomena, such as sunspots, solar flares, and coronal mass ejections. The current period, including May 2025, sees the sun squarely within its solar maximum phase. This means we are living through a time when our star is naturally more prone to unleashing powerful bursts of energy and plasma. The transition into solar maximum is marked by significant changes in the sun's magnetic behavior, including the dramatic flipping of its magnetic poles. This active and stormy state of our sun directly correlates with an increased risk of disruptive space weather events impacting Earth. The greater number of sunspots provides more potential sites for powerful flares and coronal mass ejections. Therefore, events like the X2-7 flare in May 2025 are more probable during this phase. Understanding this cyclical nature of solar activity is crucial for anticipating periods of heightened risk to our technological infrastructure, allowing us to be more vigilant and prepared for potential solar onslaughts that could affect our daily lives. Given these increased risks, the continuous monitoring of space weather is paramount. Agencies like NASA, with its Solar Dynamics Observatory, and the National Oceanic and Atmospheric Administration, with its Solar Ultraviolet Imager and Space Weather Prediction Center, play a vital role. These organizations continuously observe the sun, track active regions, and model the behavior of solar wind and coronal mass ejections. Their forecasts and alerts provide crucial lead time for various sectors to prepare for incoming space weather. This constant vigilance allows for early warnings about potentially hazardous solar events, enabling proactive measures to be taken to safeguard vulnerable systems, both in space and on the ground, a cosmic weather forecast for our technological age. Ultimately, preparedness is key to mitigating the risks posed by solar flares and associated coronal mass ejections, especially during the solar maximum. Power companies can adjust grid loads or take susceptible equipment offline. Satellite operators can put their spacecraft into a safe mode or reorient them to protect sensitive components. Aviation authorities can reroute flights to avoid regions with communication blackouts or high radiation levels. By understanding the sun's behavior, investing in robust monitoring and forecasting capabilities, and developing effective mitigation strategies, we can better protect our increasingly technology-dependent society from the inevitable outbursts of our dynamic star, ensuring resilience in the face of cosmic weather.